All right, guys. In this lesson, we're going to look at Chapter 2, Atoms and Molecules, the Chemical Basis of Life. Now, this is just a basic introductory level chemistry lesson, and so it's not really meant to give you a lot of detail about chemistry. It's just to kind of give you an overview, because in Chapter 3, we're going to see a little bit more about the organic chemistry, the chemistry for living things, looking at things like lipids and carbohydrates and proteins and nucleic acids. So this is going to give you just a basic overview of some basic chemistry. And so one of the first learning objectives that you'll see here is just to know what the main chemical elements are for living things. And so to do that, we need to know, first of all, what is an element. The element definition for an element is here. And I'm going to be kind of following along in the kind of moving through the textbook at the same time. And so if you've got your textbook, you can look on page 25 and 26. 26 mainly is where we're at. Element is any substance that can't really be broken down into any simpler substance or form by using a normal type of chemical reaction. Most everyone is familiar with the periodic table of elements. You can see that on the slide, or you can look at page 27 in the textbook, and you'll see a list of the 92 most common or naturally occurring elements. Things like hydrogen, or magnesium, or sodium, potassium, nitrogen, carbon, oxygen. All of these are elements that you can't break them down any simpler. They're already in their smallest form. One key concept that the book kind of mentions here is important to note is that 4 of these elements, carbon, hydrogen, oxygen, and nitrogen, are really what are the most common or most abundant elements in living things. In fact, they estimate about 96% of all living things is basically composed of these 4 main elements. So let's look at a few of these. Carbon. Where are you going to find carbon at? Carbon serves as the main backbone of organic molecules. And so you can, let me get back up here for a second. Get my pointer to work. Whenever you look at carbon, you can form other compounds with carbon, and they will form chains. And so, for example, a carbohydrate or a lipid is a long chain of carbon atoms connected to other molecules. Hydrogen and oxygen, well, that's important, of course, because of H2O, water. All right? And then nitrogen, a component of proteins and nucleic acids. And so proteins, we're going to talk about a lot in the next chapter. This is a building block for many things, including your muscles. And even your bone has protein fibers in it. And then your enzymes that are in the body, these are all proteins. Your hair, your nails, all these things contain proteins. Nucleic acids we'll talk about also. That includes your DNA, RNA, and also the energy unit called ATP. That's a nucleic acid. And so that contains nitrogen. Objective 2, compare the physical properties and locations of things inside of the atom, including electrons, protons, and neutrons. And then we're going to be looking at atomic number and then the mass number. So first of all, make sure you understand that the atom has a nucleus. This is different than a nucleus of a cell. It's kind of the similar concept. It's kind of in the middle of in this case, the middle of the atom. And inside of that nucleus, you'll find 2 what are called subatomic particles. Protons, which have a positive charge, and also neutrons, which have no charge at all. They're not electrically charged. Then you do find electrons. Electrons are not in the nucleus. They are outside of the nucleus, and they have a overall negative charge. And if you want to see some diagrams, you can look on page 28, and it shows you a couple of diagrams, carbon 12 and carbon 14. We'll talk about those in just a minute. One of the main things about elements is that they can be identified based on their atomic number. If you look back at the periodic table that I showed you earlier, you'll see different numbers up at the top of the periodic elements. So, for example, carbon has a big 6 listed there. On the periodic chart, periodic table, you'll see a little box has a symbol for carbon, and then up in one corner has a 6. That 6 indicates the atomic number. That's also telling you how many protons there are in one atom of carbon. All right, so 6 protons in carbon. Well, it turns out that if you have 6 protons, you also have 6 electrons, provided that this atom is uncharged, that it doesn't have any charge associated with it. The atomic mass, you can think of almost like a weight. Is basically if you take the number of protons and the number of neutrons and look at those together, you'll have what's called the atomic mass. And again, this information is given for you on the periodic table. So usually it's indicated at the bottom. And so again, if we go back and look at carbon, at the bottom, it'll say something like 12, and there's it's actually 12.01. So right around 12 is the atomic mass. So that tells us, if you take 12 and that 6 there, that you can figure out how many neutrons there would be. All right, so 6 is the number of protons. 12 is the number of protons plus neutrons. So that means there must be 6 neutrons. 6 neutrons, because 6 plus 6 is 12, and that gives you the atomic mass. That's a little different than looking at an atomic mass unit. That is, if you were just talking about the mass of a single proton or a single neutron, then that would be an AMU. Electrons, you can think of as having a very, very small mass, and you can see there that it's only a fraction of that AMU unit. All right, moving on to isotopes. Isotopes are basically the same element, although they have a different number of neutrons. All right, they have the same number of protons because the proton number determines the element. Because you have a different number of protons, you have a different element. In this case, you've got 2 elements, and again, this is on page 28. You have one element here, carbon. This is on the left. You see the natural carbon in its natural state. It's got 6 protons. Tells you down here it's got 6 protons and 6 neutrons, all of which reside in the nucleus. These are the protons here with a positive charge. These are the neutrons here. All right. So it's got a mass number of 12. That's carbon 12. Over on the right side, you have an additional 2 neutrons. So if you see here, it says 8 neutrons. And so now it has 8 neutrons in the nucleus instead of 6. So now you have a different element. You have the same element, still carbon, you just have a different number of neutrons. All right, so now it's called carbon 14. Usually what that means is that element, that isotope, may have radioactive characteristics, radioactive properties. It's usually unstable because it has more neutrons than it generally would have. All right, let's talk about electrons a little bit. What are orbitals and electron shells? All right, orbitals are basically where electrons reside. Remember, electrons are outside of the nucleus. They're not inside the nucleus along with the protons and neutrons. They're outside the nucleus, but they are contained in what are called orbitals, or sometimes they're referred to as an electron shell. Those electron shells represent various energy levels. And there's different energy levels for different atoms. And one thing to note is this statement here at the bottom that you see is that electrons in shells far away from the nucleus have more energy than the electrons in the shells that are closer to the nucleus. Right. So we'll show you some examples of that. And again, this is on page 29 if you're following along in the textbook. This shows you different types, different examples of orbitals, atomic orbitals, and shows you where the electrons may be residing. One previous model is what's called the Bohr model. This is down here at the bottom. That shows you an example of an element neon where you have different levels, different shells. And so the inner orbital here will have 2 electrons. It can only have up to 2 electrons. And then the outer layer can have up to 8 electrons. And so in this case, this neon atom has a total of 10 electrons. that orbit its nucleus. You should know the definition of what is called a valence electron. Valence electron, this is the electron that's on the outer energy level of an atom. All right, so there's your definition again, the electron in the outer shell. Remember, the further away the electron is, or the further away the shell is, the more energy that's associated with those electrons. And so that usually means those are the ones that are more reactive. And we'll talk about some basic chemical reactions in just a minute. The number and the arrangement of the atom's valence electrons determine its chemical properties. All right, determine its chemical properties. And a lot of that deals with how reactive something is. Okay, some atoms are very, very stable, such as helium. It's not very reactive. And so it doesn't react with many things. Other things, such as sodium. Most everyone is familiar with sodium because sodium chloride, these two react very strongly together to form salt. And so these are two relatively reactive elements. All right, so an atom will tend to generally lose, gain, or share electrons in order to fill up that valence shell, that outer energy level. It wants to try to fill it up. The most it can have on the outer shell, again, is 2. And so, on the inner shells, 2, most it can have on the outer shell can be up to 8. And so atoms are always trying to fill up that outer energy level with any way that it can. And it will either do that by getting rid of one, trying to gain one, or trying to share one. Right? In the process, it's going to form what's called a chemical bond. And when it does that, it forms a compound. A compound is basically chemicals that are chemically bonded together. And it gives us a chemical formula, such as, again, like I said, one of the simplest ones that you probably already know about is salt, sodium chloride. You've got 2 atoms, an atom of sodium, an atom of chlorine, that are chemically bonded together. That changes their chemical properties. If you know anything about sodium, sodium is highly reactive. It's explosive, actually. It's highly reactive. And so chlorine on its own is a poisonous gas. But if you combine these two, it forms salt, table salt. And we eat that every day. We have to have that in our diet. All right, so the little bit of information about various chemical formulas. You basically are looking at for example, the simplest formula here. You just have a whole number ratio of the atoms. And again, I keep using sodium chloride. It's just a 1-to-1 ratio. And so that's pretty easy. A molecular formula may show the actual numbers of each type of atom. And you could see that with like H2O, because you've got 2 atoms now of hydrogen, 1 atom of oxygen. Structural formula will actually show you the arrangements, how they're arranged. And so again, if you look at hydrogen and oxygen forming water, you'll see that they form kind of a shape about like this. And that's just how the bonds form. Now, a molecule will consist of atoms joined by covalent bonds. Those covalent bonds we'll talk about briefly are where those outer electrons are shared. Covalent is sharing bonds. There's other types of bonds we'll talk about, ionic bonds and hydrogen bonds. One concept that's important, you'll see this a lot in chemistry, is the designation of a mole. So here's your definition. A mole is a mole of any substance contains a specific number of atoms, and that number is 6.02 times 10 to the 23rd. That's a very, very large number. Anything and that happens to be what's called Avogadro's number. You can think of a mole, use the term mole just like we use a term dozen, right? Everybody's familiar with what the number dozen means. It means 12. Right? You have a dozen eggs, you have 12 eggs. Well, a mole of eggs would be 6, right here, 6.02 times 10 to the 23rd. That's scientific notation, but it's a huge number, right? But if you're dealing with something as small as atoms or molecules or ions, that number is actually very practical to use. So let's look a little bit about some different bonds. Number one bond is covalent bonds. First thing to note is that these are relatively strong, stable bonds. It's not impossible, but it's more difficult to break apart a compound if it is held together with a covalent bond, right? How do you form these? These bonds are formed through sharing those outer electrons, sharing valence electrons. It forms what are called molecules. All right. Good example, H2O. That is a molecule of water. You've got 2 hydrogens, 1 oxygen. They're sharing electrons on the outer energy level to form covalent bonds. Right. Here's some examples. Sometimes elements on their own will bond together. Notice here hydrogen has 1 electron on its outer energy level, and it's means that it's very reactive on its own. It wants to stabilize that. Well, for hydrogen, 2 on its outer energy level will actually stabilize it. And so what it does is it comes close to another hydrogen atom, and they create a covalent bond, and they actually are sharing those electrons, and that forms a molecule of hydrogen. Oxygen kind of does the same thing, but notice here, oxygen will have 6 electrons here and 6 electrons on this oxygen atom, but it would really like to have 8 if at all possible, and so it can share a pair of electrons here, and so now it's almost like each oxygen can assume it kind of has 8 electrons on its outer energy level, right? And so that forms, again, a molecule of oxygen. The oxygen, by the way, the oxygen that we breathe is always like this. So that's why we write oxygen as O2. Right? O2. There's a difference between how covalent bonds share electrons. If the electrons are shared equally between the 2 atoms, then it's what's referred to as nonpolar. Right? If one is not shared as equally as the other, then it's something that's called polar. And I go back to the water example. Water is a good example of something that's polar, because that's why a lot of times you see it drawn out in a chemical structure kind of like this, is because these electrons are not being shared evenly. So water is a good example of a polar molecule. All right, chemical bond number 2, ionic bonds. This is where you have electrons that are being not shared, but kind of transferred between ions. All right, so formed between a positively charged cation and a negatively charged anion. First of all, an ion is an atom with a charge. Ion is an atom with a charge, has a charge associated with it. Electrical charge. It can either be positive or it can be negative. If it's positive, then it's called a cation. If it's negative, it's called an anion. And so these substances, a good example of an ionic compound is sodium chloride. On its own, sodium would have a positive charge. Chloride would have a negative charge, and these would come together to form an ionic bond. And that's exactly what you see here in this example. Here you see that sodium is very reactive because on its valence shell, it has 1 extra electron here that is wanting to, it wants to get rid of it. It wants to get rid of that extra electron. Well, it turns out that chlorine is needing 1 extra electron to stabilize its outer energy level because it wants to have 8 electrons on the outer energy level. this wants to get rid of it because sodium wants to get rid of this one, because if it does, it would have 8 electrons here. And so what happens is one of the electrons from that outer energy level from sodium kind of jumps over here to chlorine, and that allows a transferring of electrons, and that allows this to create a bond and this to stabilize both valence electron shells. And that forms the compound sodium chloride. All right, let's talk about another type of bond, a hydrogen bond. This isn't really a chemical bond, but it is a very important bond. It's a relatively weak bond that forms with hydrogen and some other atom. Usually you'll find it with oxygen, maybe nitrogen. The hydrogen that we've been talking about for water, it's H2O. And so those will form a hydrogen bond. Yet also, hydrogen bonds are also what give the some special properties to water as well. And so if you look on page 35, it talks a little bit about hydrogen bonds and some of the weak attractions that is formed there. In the next section, here you see kind of what happens. Remember that water, the H2O molecule, is held together through the covalent bond, but you have seen here one molecule of water and then a molecule of ammonia, and the hydrogen from the water is being attracted over to the nitrogen from the ammonia molecule, and so it's creating just a little bit of a charge, a little bit of a bond, a little bit of an attraction between these two, this hydrogen and this nitrogen. Right? It doesn't form a new chemical or anything. It's not a chemical bond. It's just a little bit of an attraction. All right, other types of chemical reactions here are oxidation and reduction reactions. We're not going to go over these a lot here. We're going to pick this up mainly whenever we get into some other concepts like photosynthesis and cell respiration. You'll see what are called oxidation and reduction reactions for now. Know that one thing to remember is that oxidation is actually losing electrons, reduction is gaining electrons. So whenever something loses electrons, then you're dealing with an oxidation type of reaction. If it gains electron, you're dealing with a reduction type reaction. And there's those definitions for you. Oxidation, atom, ion, or molecule loses electron. You can associate electrons with energy, right? Electrons are energy. And so make sure you realize that, because whenever substances lose electrons, that's also losing energy. So if something becomes oxidized, it generally means it has less energy. If something becomes reduced, it generally means it has more energy. Properties of water. I'm going to go through a few things here. We have already said that water is a polar molecule, and that gives it certain properties. And of course, the hydrogen bonds that it can form, that gives it certain properties. Because it is polar, that allows it to dissolve many substances, many other polar substances. And so that, if you ever heard that water is the universal solvent, doesn't mean it will dissolve everything, but it will dissolve many other polar substances. Water also has a property called cohesion and adhesion. Cohesion, as it kind of sounds, means that it wants to kind of stick together with things. It will bind and form hydrogen bonds with each other. Water molecules also exhibit something called adhesion, allowing them to bind to substances with ionic charges. Another property of water is that it has what's called a high specific heat. In other words, it takes a lot of energy in order to change the temperature of water, whether it's up or down. If you're trying to heat up water, it takes a lot of energy input in order to do that. what that also means is that it helps water to maintain a temperature, a heat temperature for a long time, and that's important for human organisms. It also has a high heat of vaporization or evaporation. In other words, it takes a lot of energy. You have to basically reach the boiling point in order to vaporize or turn water, liquid water, into its gaseous state. And so that's a high heat. It has to be up to 100 degrees Celsius or 212 degrees Fahrenheit. Another property, because of those hydrogen bonds, is that ice, the frozen state of water, is less dense than liquid water. And so that helps living things that live in aquatic environments, because ice that forms on in the aquatic environment will, of course, float, go to the top. All right, very briefly, we'll talk a little bit. This is section 2.6. We'll talk briefly about acids and bases and I kind of define some of those. First of all, an acid, there's different ways to define an acid, but here's one definition. Acid basically is a proton donor. It donates protons. In other words, protons will come out into the solution for an acid. It goes through a property known as dissociation, right? And that allows it to split and release hydrogen ions into that solution. And we'll talk a little bit about pH in just a little bit and see what that means as far as an acid and how it relates to pH. A base, by definition, has the ability to accept a proton. In other words, it binds to, it's almost like a sponge. It will soak up the hydrogen ions in the solution and to form hydroxide ions. Acids you can think of as a property of hydrogen ions, or a concentration of hydrogen ions. The more hydrogen ions you have, the more acidic something is. So let's look at pH. pH is the negative log of the hydrogen ion concentration of a solution. So if you write that in a formula, write that out, you would see that pH is equal to the negative log, the concentration of hydrogen in a solution. It's a negative log, so as you have more and more hydrogen ions, okay, the pH becomes more acidic and the number starts to go down. Of course, you know that pH, you probably already know this, the pH scale runs from 0 to 7 and then up to 14. And anything, 7 is neutral. Anything below 7 is going to be acidic. Anything above 7 is going to be basic. And so here, again, the pH equation here for you is that the more hydrogen ions you have, it's a negative log. So the lower the number goes, it becomes more and more acidic. The less hydrogen ions you have, the higher the number goes, and it becomes more basic. One thing to note, if you don't already know, is that pH actually stands for something. It actually stands for the power or the potential of hydrogen. And so it's all about measuring how much hydrogen ions you have in a solution. So again, if you have more hydrogen ions, it's more acidic. It's lower on the pH scale. If you have less hydrogen ions, it's more basic, and it's higher on the pH scale. Buffers are important here because they help to balance out pH. They help to resist changes in pH whenever things start to try to fluctuate. These are very important for living things to be able to balance your acid and base concentrations. Last couple of things we'll look at is salts. Why is salt important? Salt basically can be defined as a compound in which the hydrogen atom of an acid is replaced by some other cation. Of course, we know salt as sodium chloride. And salts in general, but that's not the only salt. There are many different types of salts. but that's one of the main ones, at least for living organisms. That's very, very important. But it does allow for minerals to get into the body. For example, we need sodium. Sodium is very important in your nervous system and for muscle contractions. And so if you have low sodium amounts, it's also important for balancing fluids, water in the body. And so having the right salt concentration is very important for all living things. All right, please read over the chapter, use these notes and the other videos to try to help you out in the chapter, and maybe this will help you out a little bit.